Ashish Goel couldn't be here, but I'm his student, Peter Lofgren. This is joint work with Ashish Goel, with his postdoc Sid, and with Sesh, a researcher at Sandia National Labs. And I'll talk about a new algorithm for computing personalized PageRank. So motivation is personalized search on a network like Twitter or on the web. So here I signed into Twitter, and I searched for a common name, Adam, to see what would come up. Now on Twitter, I follow people who are in technology or computer science. So I might expect computer scientists to go on top. But the algorithm is not very personalized. The top result is a singer-songwriter, and the second top result is a guitarist. If we take the top 100 results returned by Twitter and resort them by personalized PageRank, we get this list. The top result is now the CTO of Twitter, and the second top result is the CEO of Corel. So you can see that personalized PageRank can provide better personalization, at least in this example, than the global algorithm that Twitter uses. And they're aware of personalized PageRank, but in the past it's been expensive to compute. So we're trying to make personalized PageRank cheap enough to compute that we could use it for personalized search. Now as background, I'll go through this quickly since we just had a talk about PageRank and personalized PageRank. As everyone has seen, I'm sure, global PageRank can be defined in terms of random walks and in solution to this matrix equation. And this vector u for global PageRank is a uniform vector. It's 1 over n. In the original paper, they noticed that you can replace u with a personalized vector p. For example, on the web, if the user is interested in computer science, you could have p be non-zero on computer science pages and 0 everywhere else. And the importance of those computer science pages would flow around the network. In this, our algorithm can handle arbitrary vectors p, but for concreteness, we think of p as having a single value s. So in the Twitter example, I'm a node in Twitter. I have out neighbors and in neighbors. So it makes sense to personalize just to me as a node s. But in general, our algorithm works just as well and unchanged for an arbitrary personalization in vector p. So here's this example of personalized PageRank. This red node is taking a random walk from the start node s on the bottom. 20% of the time, it's jumping back to s, and 80% of the time, it's going to random out neighbor. If you run a million of these walks and see the distribution of where the red node stops, we get this result. There are several short paths from the bottom node to the top node. So there's a tie personalized PageRank for the top node, representing an interest. Whereas on the right, there's only one path and it's long. So there's a smaller personalized PageRank value. So if we did a personalized search, personalizing the bottom node, we'd want that red node to be higher in the results than the white nodes. So defining personalized PageRank exactly as in the other talk, we take a random walk from S. After every step, with probability alpha, we stop. With probability 1 minus alpha, we continue to random out neighbor. And the personalized PageRank is the probability that this single walk ends at T. The personalized PageRank from source S to target T. And you may have seen personalized PageRank as the fraction of time we spend at node T versus the probability of ending at T. And those are equivalent. But for understanding our algorithm, it's best to think about a single walk and the probability that it stops at T. Now, there are several natural problem formulations for personalized PageRank. We might be given a single source, and we want to compute personalized PageRank to all the targets. For example, Monte-Carlo or the push method that David mentioned are useful for this. And this is useful in recommendations. On Twitter, if they want to recommend followers to me, they can start at me and do some random walks or some pushes and find nodes that have high personalized PageRank to me. In personalized search, we might be given a set of, say, 100 targets, and we want to compute the personalized PageRank from the source node to each of those 100 targets. And this talk we consider a simpler version of this problem where we have a single source node S and a single target T, and we want to compute personalized PageRank from that one S to that one T. We expect that our algorithm will generalize to the middle case, and we're working on future work for that. But for this talk, we assume that we have a single source S and a single target T, and all we care about is the value pi st. And the difficulty of this problem depends on the size of the probability that we're measuring. If S and T are right next to each other in the graph, say T is an out neighbor of S, then a few random walks, or a few one push even, will find that probability immediately. Whereas if S and T are on opposite sides of the graph, then known algorithms must explore a large amount of the graph to find that low probability path from S to T. So you have a threshold delta, which captures this issue. And we only care about personalized PageRank if it's bigger than delta. So if pi_st is less than delta, our algorithm will say that it's small, but it does not need to return an accurate estimate. But if pi_st is bigger than delta, if it's not too small, we guarantee that it will return an accurate estimate in terms of relative error. And our goal is to solve this problem as efficiently as possible. So we're trying to minimize running time while giving an accurate estimate in relative error. So in this talk, I'll describe some prior work that we build upon. I'll describe our algorithm. I'll describe some experiments that measure its runtime and accuracy. I'll sketch why our algorithm is correct. All the details will be in our paper, and it is in our paper and archive. And I'll describe future work. Okay. Now I'll describe two previous algorithms, both because we compare against them in runtime, and because we build upon them and use them as subroutines in our new algorithm. Okay. Okay. So first I'm going to preview the results that we have. So this is running time. Each of these groups of bars is a graph. And I'll explain later what graphs they are. And the y-axis is the running time of algorithms. So you compare our algorithm in blue to local updates in orange, which is a local version of power iteration, and Monte-Carlo in green, like sampling random walks. And this is a log scale. Each horizontal bar is a factor of 10 improvements. And we find that in every graph, our algorithm is 20 times faster for a random source-target pair. Okay. And these other algorithms compute more than just pi_st. They might compute from pi to all the targets, or from one target to every source. We're comparing them for a single pi_st. So that's the problem that we're focusing on. Okay. And to understand the log scale, if we move it, the running time looks like this. On Twitter, the local update algorithm is taking about an hour. Monte-Carlo is taking about 5 minutes. And our algorithm is taking less than 3 seconds on average. Okay. So now I'll describe these previous algorithms that we build upon. One is Monte-Carlo. We're estimating the probability that a walk stops at t. So the most natural thing to do is to take sample random walks and see what fraction of them hit t. If we're finding a probability of size delta, then we need to sample O of 1 over delta random walks to get a good confidence bound. So the running time of this algorithm is O of 1 over delta. And again, delta is the smallest probability that we care about. It's only guaranteeing accuracy if the personalized PageRank is bigger than delta. Okay. The other prior algorithm we use is local update. So this is similar to the push algorithm that David mentioned. Only instead of pushing forward from the source node, we push backwards from the target. We can look at the in-neighbors of the target and say each in-neighbor has some probability of going to the target immediately, and then keep pushing to the in-neighbors of those nodes. I won't have time to describe it completely, but I'll say 3 things about it. So it's a local version of power iteration. We choose nodes and we push their probability backwards. And it gives an estimate from every source that we reach to the target node t. So for all these nodes in gray, we have an estimate of the probability of a walk starting at them, ending at the node t, through a single target. And the running time of this algorithm from some prior work, it depends on the target node, actually. So the target node is someone like Barack Obama on Twitter. He has millions of in-neighbors. So expanding this push operation at Barack Obama takes millions of RAM updates and takes a long time. Whereas if the target has no in-neighbors, the algorithm terminates immediately. So it depends on the target. We can say that for random targets, the running time is O of d bar over delta, where d bar is the average degree of our graph, and delta is that probability threshold that we're measuring. Or I guess in this case, it's the additive error guarantee, which is equivalent to the smallest probability we can detect. Okay. And so the challenge is that both of these algorithms require time omega 1 over delta. And the average value of personalized PageRank is 1 over n. So you want values of delta around 1 over n. If we're doing personalized search, we have some experiments that show that you want values of delta around 1 over n in order to get non-zero answers or to get good estimates in an application like personalized search. So when delta is 1 over n, then an algorithm that takes time 1 over delta is too slow for real-time search, and we want something faster. Okay. And our result is that we can do this in time 1 over square root delta times square root d bar, where again d bar is the average degree of our graph. We state this result. We state that with probably 99%, we can get a 10% relative error, but those two parameters are arbitrary. In our paper, we have the full running time. Okay. So we can guarantee a small relative error in time 1 over square root delta times square root d bar. And delta here is the important term. Delta is something like 1 over 100 million, whereas d bar is like a few hundred. So, and the square root of that is like 10 or something. And so going from 1 over delta to 1 over square root delta is a large improvement when delta is something like 1 over 100 million. Okay. And we also prove a lower bound of omega 1 over square root delta for this problem. So our result is close to optimal. The only difference is that average degree term d, which is fairly small in most large graphs, which are sparse. Okay. So to understand how we get this square root improvement, going from 1 over delta to 1 over square root delta, we can think about an analogy to bidirectional search for shortest path. If we find a path of length L on a directed graph, and each node has degree d, then breadth first search will take time roughly d to the L to find this path of length L. Whereas if we do a bidirectional search, going backwards from the targets L over 2 steps, and forward from the source L over 2 steps, and intersecting, that takes time O of d to the L over 2, which is O of square root d to the L. So you see the same improvements of going from d to the L to the square root d to the L. Our algorithm does the same thing for personalized PageRank. Only now, instead of doing path distance, we're doing probability. So we say that a node is close to the target, but the probability of a random walk from that node stopping at the target is bigger than square root delta. When we find in our algorithm, we start by finding these nodes in gray, which are close to the target. We call them the target set. Again, those are the nodes that have probability greater than square root delta of hitting the target. They have a high probability of hitting the target on a random walk. Then we need to do one step further and find these blue frontier nodes. These are nodes that are not close to the target, but they're one step away. One of their out neighbors is close to the target. This is close in probability. Once we've computed this frontier, we sample random walks from the source node, 1 over square root delta of them. And if the ith walk hits the frontier before stopping, then we don't sample the rest of the walk. Instead, we simulate the rest of the walk and say that it has probability, it has a known probability of hitting the target. If it hits the frontier at node u, then we have a pre-computed estimate of pi ut, the probability of going from u to the target. So instead of sampling the rest of the walk, we cut it off when it hits the frontier and use our pre-computed estimate as a probability that that walk would hit the frontier, or would hit the target node if we continued it. If a walk doesn't hit the frontier and it stops first, then it has probability 0 hitting the frontier. So writing that down, our algorithm has 4 steps. The first step is to compute these target sets, to run local updates and push probabilities backwards from the target, and find all the nodes that have probability bigger than square root delta reaching the target, as well as an estimate of a random walk going from those nodes to the target. Then we can define the target set, big T, for all nodes that have probability bigger than square root delta of going from them to the target node. And the frontier, treat all nodes that are not in the target set, but one of their out neighbors is. So once we've computed this target set and frontier around the target node, this frontier is a barrier between the source node and the target. We take random walks, 1 over square root delta of them, from the source node. And if a random walk hits the frontier, then instead of sampling the rest of it, we use our estimates going forward. And if it doesn't hit the frontier, then we add probability 0 of hitting the target. This gives us these variables, random variables xi, and we return the empirical mean of these xi random variables. Okay. So now let's consider the running time of this algorithm. It has two parts, the reverse part and the forward part. The local update part takes time O of d over square root delta from prior work. The forward work takes time O of 1 over square root delta, the Monte-Carlo. So together, this is our running time. And a more improved implementation can balance these terms and get time O 1 over square root delta times square roots d. And I'll talk a bit later about how that works.
Is this independent of the size of the graph?
Yes, all our running time results are independent of the size of the graph. They're like local algorithms that expand around the targets, around the source node. And they don't care how big the graph is or how many edges it has.
And it doesn't matter how many edges there are between source and target?
No. But this is for a random target. I should say that again. For a target like Barack Obama, like it's more expensive to run this algorithm than for a target with no in-neighbors. This is for a uniform random target. Are there other quick questions about the algorithm? Okay, now I'll talk about the experiments that measure the runtime. We use 6 different data sets for a good variety. 3 of them are undirected, the DBLP collaboration network, and the Lab Journal and ORCID social networks. And 3 of them are directed, the POCEC and Twitter social networks, and a web graph from the UK. And they range in size from a few million edges to a few billion edges. And now, each of these algorithms have some parameters that change the accuracy. Like for Monte-Carlo, we could run more walks and get more accuracy at the cost of lower runtime, or run fewer walks and get less accuracy at the cost of, or get less runtime. And we choose parameters such that the relative error across the algorithms is pretty similar. I'll show that in the next slide. We choose fixed parameters so that the accuracy is comparable, and then we can fairly measure the runtime and compare the runtime. And we measure the relative error, the empirical relative error for each of these algorithms by sampling random sources and targets, computing the true PPR to a high accuracy, and then running the 3 algorithms to measure the accuracy. And then once we've chosen our parameters, we load the graph into RAM. And for each algorithm, we sample source target pairs and run each of the 3 algorithms for those source target pairs. The accuracy is here. This is mean relative error across those source target pairs. And you can see that they're comparable. They're all less than 15% at these parameter settings. And to be conservative, we made sure that our algorithm was more accurate. But the main result is that at the same parameter settings, our runtime is much faster. It's 20 times faster on all the graphs per ST pair, per random ST pairs. And this is still log scale. Each horizontal line is a factor of 10 improvement. The running time depends on the global PageRank of the targets. Like I mentioned, Obama will be slower than a new user with no in-neighbors. So here we sorted all the targets by their global PageRank, and we plotted them left to right. So on the left, we'll have a node like Obama with the highest global PageRank in 2010. And on the right, we'll have we have nodes with no in-neighbors at all. And we plot the runtime of these 3 algorithms, plus an improved version of our algorithm. So the red line is running time of local update. For a high global PageRank node, it's very slow. It's taking several hours. Whereas for a node with no in-neighbors over here, it's taking less than a millisecond. It's very fast. The cyan line that's constant across the top is Monte-Carlo. It doesn't care who the target is. It just runs 1 over delta random walks, or O1 over delta random walks, and measures what fraction of them hit the target. The blue line is our algorithm. For the worst node, it's taking like 30 seconds. And then it quickly reaches less than a second for like 95% of nodes. But it's still not beating local updates in the right part of the graph. Because even if the target has no in-neighbors, it's still doing big O of 1 over square root delta random walks. So that inspired us to create a balanced version, which creates this green line. And the balanced version changes the amount of forward and backward work to balance them. So earlier, I defined this gray set through the set of all nodes that have probability bigger than square root delta of hitting the target. Well, we could change that. We can make it 1/10 square root delta or 10 square root delta. We can make the target set bigger and do fewer random walks, or make the target set smaller and do more random walks. And this balanced FAST-PPR algorithm in green does that. It sort of dynamically chooses the right size of the target set such that the forward work equals the time spent doing backwards work. And in our paper, we describe exactly how that works. Now we'll talk about the correctness of our algorithm. And the key observation for understanding our algorithm is that every walk from the source to the target must hit the frontier. And it hits the frontier for the first time exactly once. Because the random walks are memoryless, once a random walk has hit some node u in the frontier, we don't care where it came from. We can compute pi ut independent of where it came from. So this gives us a decomposition. So that the probability of a walk going from the source to the target and stopping is the sum over all nodes in u in the frontier of the probability that that walk hits that node u first in the frontier times the probability that a walk from u goes to the target and stops. And if our estimates from the frontier forward, these pi ut estimates, are perfect, then these estimators xi are unbiased, perfectly unbiased. And then some standard Chernoff bounds show that with O of 1 over square root delta random walks, we can get concentration of this estimator. And an important point here is that each xi is in the interval 0 square root delta. So in Monte-Carlo, we run random walks until they hit the target. And then they score either 1 if they hit the target or 0 elsewhere. So because each random variable is in this big range 0, 1, there's high variance on each one, and it takes a lot of samples to get a good concentration. Whereas here, each xi can only contribute a square root delta term to the sum. And so we need fewer of them, only O of 1 over square root delta of them to get concentration. So one question we asked when making this algorithm is whether the frontier was actually necessary or not. It'd also be natural to find the target sets, the nodes that are close to the target, and just run random walks until they hit the target sets, rather than going one step further with the frontier. But it turns out that the frontier is important both in theory and in practice. So in practice, on the left, we sampled random source-target pairs. And on the x-axis, we have the true personalized PageRank. On the y-axis, we have the estimates returned by our algorithm. So a perfect algorithm would have all points on the line y equals x. And you see that our estimates are very close to that line. Whereas if we remove the frontier and run our random walks until they run into the target sets, we get this plot. There are two things that can happen in this case. One is that since the target set is smaller than the frontier, the walks might all miss the target set. And then that's these points down here that have an estimate of 0. Alternatively, because the probability from the target set to the target node might be very large, if the random walks hit the target set a few more times than expected, we get a big overestimate of the probability. Because the frontier was essential to our algorithm, we named it frontier-aided significance thresholding. Okay. And now, to prove accuracy, there's actually a theoretical issue with the algorithm I presented. And that is that local update gives an additive error bound, like an L infinity bound. And for nodes in the frontier, that does not translate to a relative error bound. Only for nodes in the target set does that additive error translate into a small relative error. And so while the algorithm I presented works well in practice, and that could generate the empirical relative error I showed you, in theory, you need a more complicated algorithm. So I won't have time to describe it fully, but I can give the main idea of it. If we run a random walk till it hits the frontier, in the next step, one of two things could happen. We could go to the target set, and then from there forward, we would have a good estimate. Or we could not go to the target set. And so in the advanced version, when we hit the frontier, we break it into two cases. We have some term for the probability that we could have gone to the target set, and then we accumulate the probability going forward from there. And then there's also the option that we could not go to the target set. And for that, we sample an out neighbor, which is biased to avoid the target set. And we continue this random walk. And because our random walk is biased to avoid the target set, we have to add some correction terms to the probabilities and to the transition probabilities. The details are so technical, but you can read about them in our paper, which is on arXiv. Okay. So future work. One future work would be, okay. We described the algorithm today as running on a single machine with the graph in RAM, but in a system like Twitter, you'd want a system with a lot of machines running in parallel. And so there's a version of our algorithm where you can pre-compute the frontier from each target and pre-compute the random walks from each source. And then at runtime, you just dot together these two pre-computed values. And that's much faster and more scalable. Or is it? Yeah, more scalable. And then from that, someone can create a personalized search system based on this. A more theoretical future work would be matching lower bounds and upper bounds. I mentioned how we proved that the running time has to be at least omega 1 over square root delta, but our algorithm runs in time square root d over delta. And in practice, d is fairly small, so it's not really an issue. But if you wanted to run this on a dense graph, or like have a theoretical matching bound, it'd be interesting to either find a better algorithm or find a better lower bound. And after David's talk, I'll mention another example, another extension would be extending this to the heat kernel or to other distributions on lengths. Okay, thank you.